Cikgu 360 Torque in Mechanics. Let's go!
Hi. So, I am Jo and Hannah. So, in this topic, which is torque, I'm going to explain to you guys what is the definition of torque.
Hello! Today, I'm going to explain what is torque. Torque is the turning effect produced by a force acting at a distance from a pivot or rotation point. In simple words, torque tells us how effectively a force can rotate an object. Torque is represented by the Greek letter, which is tau. When you push a door near the hinge, it is harder to open, but when you push far from the hinge, it becomes much easier. These differences happens because of torque.
So, let's move on to Haziq.
Thank you, Hannah, for your explanation about torque. And I want to tell you guys, every time that you guys learn about the topic in physics or maybe in mechanics, there must be formula in it. So, right now, myself and I, Muhammad Haziq and Muhammad Fazli, will tell you guys about the formula about torque. Right? So, without further ado, let's get into it.
Right, so right now, I'm gonna teach you guys about the torque formula, force at a distance, which is the formula that you guys need to know in this subtopic, which is torque. Alright, so this is the formula, force at a distance, which is torque is equal to F times R sine theta, and torque, the unit SI is Newton meter, equals to F, which is stand for magnitude of the force applied, and then R is the total length of the arm of the lever in meter, and then the theta is stand for angle between the force and point in degrees, or we can say the angle between the force and the length of the arm of the lever. Alright, but there is another case that the formula torque that already simplified, which is when the force is applied at 90 degrees, torque is maximum. In that case, sine 90 equals to 1. So the formula becomes simplified, which is torque equals to F times R. Torque equals to F stand for force and R stand for radius. Alright, so if you guys know, torque is the vector quantity, and then torque there must be has the direction. So we can determine the direction of the torque by using right hand rule. As you guys can see here, this is the example. Alright, when you guys using the right hand rule and then you guys curl your hand inside, by following the rotation of the direction, your thumbs and your hand will show where is the magnitude of the torque. Alright, so that's only the formula that you guys are gonna learn in this subtopic, which is torque.
And I'm Siti Nurul Idayu. We hope this video will help you learn about torque. So, let's begin! Now, we know that torque also causes rotation. Torque also has direction. There are two types of torque. First is the anti-clockwise torque. It rotates an object anti-clockwise and is usually taken as positive. Second is the clockwise torque. It rotates an object clockwise and is usually taken as negative. This direction is important because later, in equilibrium problems, we compare clockwise and anti-clockwise torque. Now, let's watch a simple video to see the direction of torque.
The right-hand rule can determine the direction of torque. If you curl the fingers of your right hand in the direction of the rotation caused by the force F, your thumb will point in the direction of torque.
Assalamualaikum. My name is Adana Fitri bin Zainal Abidin and I will explain about thought in equilibrium. Before I start, I would like to ask one question. Do you guys know what is meant by equilibrium? In mechanics, equilibrium means that the object is stable and does not rotate. In this section, I will explain what thought equilibrium is and how it happens in real life situation. So, what is thought equilibrium? Thought equilibrium happens when an object does not rotate, even though forces are acting on it. This means the object is balanced around the pivot point. Therefore, thought equilibrium describes a condition where rotational motion is prevented. For an object to be in rotational equilibrium, there is one important condition, which is the total anti-clockwise torque must be equal to the total of the clockwise torque. For this can be written as the sigma torque anti-clockwise equal to the sigma torque clockwise. If this torque are not equal, then the object will rotate to the larger torque. For example, if the total torque in anti-clockwise is larger than total torque in clockwise, then the direction will go to the anti-clockwise. Yes. So, torque equilibrium can be seen in many real-life situations. For one example is a seesaw balance. On the right picture, there is a same weight and the same distance from the pivot point, while in the right picture there is a object that have a different weight but still can sitting balanced by the different distance from the pivot point. So that's all for me. Let's move on to the example question.
In this video, I will explain step by step how to determine the tension in the supporting cable and the force acting at the hinge for the static problems. So, the system is in static equilibrium, which means it is not moving and not rotating. So, we are given a horizontal strut that is 4 meters long and it is attached to a wall by a hinge on the left. A 400 Newton signs hang from the right end of the strut. So the strut itself has a weight of 600 Newton. Since the strut is uniform, its weight acts at the center of the strut, which is 2 meters from the hinge. A supporting cable is attached from the right end of the strut to the wall 3 meters above the hinge. So we are going to find the angle of the cable. The cable, the wall and the strut form a right angle triangle. The vertical height is 3 meters and the horizontal distance is 4 meters. So it's forming a 3-4-5 triangle. So we are going to use the trigonometry, which is tan theta equals to 3/4. So theta equals to tangent inverse 3/4. We are going to get 37 degrees with the horizontal. Next, we are going to draw a free body diagram of the strut only. The forces acting on the strut are first, the weight of the strut is 600 Newton acting downward at the center. Next, the weight of the sign is 400 Newton acting downward at the end. And then the tension in the cable T acting at 37 degrees at the end of the strut. Lastly is the direction force at the hinge, which will resolve into a horizontal component FHX and a vertical component FHY. Then, because of the strut is in equilibrium, then the sum of horizontal forces is 0, the sum of vertical forces is 0, and the sum of moments above any points is also 0. So we will start with the moment equilibrium as the simplifies of the problem. So why we take moments about the hinge? We take moments about the hinge because the horizontal and vertical hinge forces pass through the hinge and therefore they produce no moments. This allows us to eliminate the unknown hinge forces from the moment equation. So, the moment is calculated as force times perpendicular distance. So, the clockwise moments are the strut's weight is 600 times 2 equals to 1200 Newton meter, and the sign's weight is 400 times 4 meter equals to 1600 Newton meter. So the total of the clockwise moment is 1200 plus 1600 equals to 2800 Newton meter. So the only forces that producing an anti-clockwise moment is the vertical component of the cable tension Ty, which is acting at a distance of 4 meter. Anti-clockwise moment is Ty times 4 meter. So for the equilibrium, the clockwise moment is equals to anti-clockwise moment. So 2800 equals to 4 Ty. So Ty equals to 700 Newton. This value is the vertical component of the cable tension. So now we are going to find the total tension in the cable. The vertical component of tension is related to the total tension by Ty equals to T sine 37 degree. So T equals to 700 over sine 37 degree and T equals to 1163 Newton. Therefore, the tension in the cable is 1163 Newton. So the total downward force is the weight of the strut plus the sine. So 600 plus 400 equals to 1000 Newton. We are going to apply the vertical equilibrium. So FHY plus Ty equals to 1000. So FHY equals to 300 Newton upward. So horizontally, the forces are horizontal component of cable tension, which is Tx, and horizontal reaction force at the hinge FHX. So FHX equals to Tx equals to T cos 37 degree. So FHX equals to 929 Newton. So the hinge force has both horizontal and vertical components. We are going to use the Pythagoras theorem. So FH equals to 929 square plus 300 square equals to 976 Newton. So the direction of the hinge force is the horizontal component is much larger than the vertical component and points towards the wall. So by physics convention, 0 degree is to the right and 180 degree is to the left. Therefore, the force at the hinge is 976 Newton at 180 degree. So the conclusion for the example is the tension in the supporting cable is 1163 Newton, while the force acting at the hinge is 976 Newton at the 180 degree. So the system is in equilibrium because all forces and moments are balanced.
Okay guys, so right now let's make a numeric example. Since I already teach you guys about the formula in torque, and right now let's apply in this question. Alright, first let's read the question first. A 2 meter long bar has an axis of rotation located at the center of its length. A force of 5 newtons is applied 0.5 meter to the right of the axis. It acts at angle 75 degree to the bar, causing a counterclockwise. The second force of 2 newtons is applied at the end of the bar to the left of the axis rotation. It's an angle 90 degrees, causing a clockwise torque. What is the sum of the torque of the bar? Alright, first of all, if you guys want to answer this question but the question is not giving you a diagram, first of all, you guys need to draw your own diagram so you guys can see more visual. Alright, so let's follow me. Alright, so first of all, a 2 meter long bar means that there's a 2 meter long bar here. Okay, and then has an axis of rotation located at the center of its length. So means that at the center of its length there is an axis of rotation. So since there is a 2 meter, so each side have 1 meter long, like that. Okay, and then the next one is a force of 5 newton is applied 0.5 meter to the right. So means that at the right there is a 5 newton applied. So means that the length here is 0.5 meter. It acts at an angle of 75 degrees with the bar causing a counterclockwise. So counterclockwise is like this, okay, and then it's like this. That is more going to upward. So it says that 75 degree, right? So from here to here, and then we draw a 75 degree, alright, just like that. And then enough with the first part. For the second force is 2 Newton is applied at the end of the bar to the left. So means that at the left and 2 Newton is applied is right here. So means that there is 2 Newton here. And then he said that it acts an angle of 90 degree causing a clockwise torque. So clockwise torque is like this. So it means it's go downward. And then it say that 90 degree. So we just draw a straight line here and then 90 degree. Alright, so we are done drawing a diagram. And then it is make us more easier to answer this question. Alright, let's move to the next step. And then first of all, you guys need to determine the known values such as the radius, magnitude of the force, and the angle and direction in which they are applied to the object. Let's make for the 5 Newton first. Alright, for the 5 Newton, we can hit it here. For the 5 Newton, we are given the radius is 0.5 meter. Alright, so this is the radius. And then to the right of the axis, and the angle is 75 degrees. And then counterclockwise. So by convention, counterclockwise is the positive direction. Okay, counterclockwise is the positive direction. Alright, so let's move into the next one. For the 2 Newton, we are given radius of 1 meter. See, from here to here is 1 meter. Alright, so the radius is 1 meter. And then for the for the angle is 90 degrees. That is 90 degrees. Alright, so now and then the question said it is a clockwise direction. So by convention, clockwise is the negative direction. So you need to know it is a negative direction and this one is a positive direction. Alright? Alright. Next, step 2 is set up the specific equation for the sum of torque. So means that the sum of torque is equal to the first torque plus the second torque. Alright? And then it set the value for the individual torques including the proper sign of their direction. Right? So as we know, the formula of torque is R1 F1 sin theta 1 plus R2 F2 sin theta 2. Okay? So after we already write this equation, we just fill in the number that already we write it at here. Okay? And then so the first radius is 0.5 meter. 0.5 meter. And then the force is 5 Newton. And then sine 75 degree. And then we need to remember the sign is the positive direction. So let's just be there. And then the second one, it is the negative direction. So we need to put here negative. Okay? So the radius is 1 meter, and then the force is 2 Newton, and then sine 90. Alright, so after we already write this equation, we just use your guys' calculator to get the answer. Alright, so let's calculate the net of the torque, and then if you guys use your guys' calculator, you will get here 2.4 Newton meter, and then here is a minus 2.0 Newton meter, and then the answer is 0.4 Newton meter. But that is not finished yet. As you guys can see here, the answer is positive. So, means that this result tells us that the sum of the top on the bar is positive. So, it is a counterclockwise direction. Okay, 0.5 millimeter, and then you guys need to say counterclockwise direction. Okay, so that's all for this question. I hope you guys understand.
Now, I will demonstrate a simple thought. It's a door. When I push near the hinge, it's difficult. But when I push far from the hinge, it's easy. Because torque increases.
I will demonstrate how a manual scissor car jack works using torque. On the right hand is where we apply force. The distance from this point to the pivot determines the torque. The pivot is located at the center of the jack. This is how I lift the car upward. By turning the handle clockwise, the torque rotates the screw, and with minimal effort, the car lifts easily. To lower the car, I turn the handle anti-clockwise. The motion reverses, and the car comes down smoothly. That's all for demonstration.
In conclusion, torque is the turning effect of the force.
It depends on the force, the distance from the pivot, and the angle of the application.
It is essential in understanding how objects rotate and how tools work.
Thank you for watching our presentation on torque.
Bye!